Hello and welcome back. In this video we're covering section 3.2. So we're going to be graphing lines this time. Last time we were focusing just on plotting points, and we kind of ended up with an example that implied the shape of the full line of a equation in two variables. So this time we're going to be graphing full lines by either plotting points and connecting them together, um, or by finding intercepts, which are some special points that can help us um, kind of anchor the position of a line in the xy Cartesian plane. So first, let's just try getting some points together and plotting them and graphing our line. And I mentioned this at the end of the last video, but if we have some line in two-dimensional space, so this is an x-axis and a y-axis, and let's just say in general we have some line. Maybe it looks like this. And there's some equation that represents this line. And since we're staying general, I'll just call it ax plus by equals c. And we'll come up with other forms of lines as well. And I mentioned last time that every point on this line, if we were to locate a single point on this line, it represents a solution to the equation, some x value and some y value that makes it true. And there's an infinite number of points on this line. It goes on forever in both directions. So that implies that there's an infinite number of solutions for a given linear equation in two variables. So that's what this first property is saying. Every linear equation in two variables has an infinite number of solutions, and the solutions are ordered pairs, meaning we can represent them as points. And maybe going a little bit backwards, but the graph of a linear equation, so this is a general linear equation, ax plus by equals c, is a straight line, meaning it's not curved. Part of the definition of being linear. And each point on the line is a solution to the equation. Probably should have had these flipped. So let's look at an equation and graph it just by getting a few points together. Notice if we just know at least 2 points on the line, we'll be able to know what the line looks like. So let's try that. Let's get a few points together. So in example 1, they want us to graph negative x plus 2y equals 4. So we're applying this method, where we're going to find points. We're going to plot them and connect it with a line. Specifically a straight line. So let's build a little table of values like what we've seen previously. So some x values and some y values. And let me write down our equation again. Negative x plus 2y equals 4. So let's just pick some x values and find out what the associated y value will be. Let's start with 0. 0 is usually a really easy value to plug in. So I can say when x equals 0, and then let's plug in 0 for x, so negative 0 plus 2y equals 4. Negative 0 is just 0, so this just reduces to 2y equals 4. Then I can divide both sides by 2, y equals 2. So I should have the point 0, 2 on our graph, 0, 2. Let's pick another x value, maybe like 2. We can pick any value we want. So I can say when x equals 2, let's plug this in. This will be negative 2 plus 2y equals 4. So that'll be negative 2 plus 2y equals 4. Let's add that negative 2 over. So 2y will equal 6. And then divide by 2. 6 divided by 2 is positive 3. So we plugged in 2 for x and got 3 as the y value. We should have the point 2 comma 3. And then let's pick another point, maybe something negative, like negative 4. So let's say when x equals negative 4, so I'm plugging into x, so I already have a negative, and this is part of why I use parentheses to help me see. I'm going to have a double negative there. So negative 4 plus 2y equals positive 4. The double negatives will cancel. It'll just give us positive 4 plus 2y equals 4. And then we'll subtract the 4 over. 4 minus 4 is 0, so we get 2y equals 0. And then when we divide both sides by 2, 0 divided by 2 stays 0. So that gives us the point negative 4 comma 0. So let's plot these. Let's make a little graph. So I'll draw my axes first. I know I want to go out to negative 4 over there. I think I'll go 4 in each direction. Let's make it a little bit farther. 1, 2, 3, 4. 1, 2, 3, 4. 4 in this direction. 4 in this direction. And again, this is x-axis for the horizontal and y-axis for the vertical. So let's plot these 3 points. We have our first point, 0, 2. So 0 in the x direction, 2 in the y will be up here. 0, comma 2. Then 2, 3. So 2 in the x direction, and then 3 in the y direction will be up here. So this is 2, comma 3. And then we also had the point negative 4, 0. So over here at negative 4 for the x value, and then 0 for y, meaning we're staying on the x-axis. Negative 4, comma 0. And then these look like they're lining up pretty nicely, so let's just connect them with a straight line. Something like this. Oops. Sometimes I accidentally hit the buttons on the side here. So we got 3 points. We only really need 2 points to plot a line. The textbook likes to use 3. I think the third one is like a backup. Just in case something went wrong. You can verify they're all 3 on a line. And notice we have 2 special points where it crosses the x-axis and where it crosses the y-axis. So we would call those intercepts. Let's say the point 0, 2 is a y-intercept. Meaning it's crossing the y-axis at that point. And notice that's where x is equal to 0, because we don't move anywhere in the x direction, and we just are somewhere on the y direction. And then over here, we have an x-intercept. That's what I'll call that point, at negative 4, 0. I can say negative 4, 0 is an x-intercept. Just to label some interesting points here. But again, there's an infinite number of points on this line. So that's one method. We can just pick a few x values. We could have picked y values as well, whatever y values we want. Plug them in and see what we get. But we can also focus just on these intercepts because it ends up being easy to plug in zeros usually into an equation. So that's our next method. Graphing a linear equation in 2 variables by finding the intercepts. So the text gives us some definitions, and then also again just to visualize, let's imagine some random line. Let's say it looks something like this. This is our x-axis and this is our y-axis. So it says the x-intercept of a graph of an equation is the point where the graph intersects the x-axis. Sounds legit. So yeah, there on the x-axis, that will be our intercept point. We can describe it as some x location, but notice the y value would be 0 because it's on the x-axis. And then we can similarly describe the y-intercept as the point where the graph intersects the y-axis, so down here. So we could label another just general point. It has 0 for the x-coordinate because we haven't moved anywhere horizontally. We're staying on the y-axis. And it has some y-coordinate. I'll just call it y since we don't know exactly where it is yet. So this implies a technique that we could use. Again, we'll call this the x-intercept. Just abbreviate with int. And then we'll call this the y-intercept. So this location of the zeros implies a technique we can use to find these points. So let's look at this example and I'll show you what I mean. So our equation is y equals negative 1/3 x plus 1. It says to graph by finding intercepts and another point. So here's our method. If I want to find the x-intercept, so I can say to find the x-intercept, we said earlier the x-intercept occurs when y is equal to 0 because we're on the x-axis. So we can just use that as a y value. We can replace y with 0. Then just solve for x. So let's do that. I can say when y equals 0, we would have 0 equals negative 1/3 x plus 1. So let's just solve for x. We can subtract the 1 over to the other side. This would be negative 1 equals negative 1/3 x. And we can see this, it might be easier to see this as like negative x divided by 3. We can move the x up in that numerator. And it's a little bit easier to see that I want to multiply the 3 over to the other side. And let's multiply by negative 3, so we'll deal with the negative at the same time. So this will turn this into a positive 3 over here, because negative 3 times negative 1, make it positive 3. So negative 3 equals x. Let me swap my colors here, because I usually use purple for the math work. Okay, so that tells me when x equals 3, y equals 0. We plugged in 0 for y and found the x value equals 3. That's going to be our x-intercept. So we get 1 point. So let's do the same thing for y. So we can say to find the y-intercept, you can probably see where we're going with this, but remember the y-intercept occurred at an x value of 0, because we're on the y-axis. So let's just plug in 0 for x. So to find the y-intercept, replace x with 0, then solve for y. So we're doing the opposite. So I can say when x equals 0, we would get y equals negative 1/3 times 0 plus 1. Well, the 0 will just delete the negative 1/3. So we get y equals 1. So that tells us we said x was 0, and we got 1 for y. So 0, 1 is our y-intercept. So let's use these 2 points and plot our line. So I'll build my axes. Add some markers. Go out to 4 in each direction. So we have 3, 0 as our x-intercept. And again, this is our x-axis. Vertical is our y. So at positive 3, 0, we should have a point here. And then our y-intercept was 0, 1. So at positive 1 on the y-axis. So let's just connect it with a line, and we'll have our graph. And we could, if we wanted another point, we can just pick another x value, any value we want. Or we could pick a y value, plug it in, and we should get another point on this line. So it can be a pretty quick method for plotting a line. Just find the 2 intercepts. Sometimes the points can be a little bit tricky if they end up falling in between values, if you get like a decimal. But notice this pattern for finding these 2 values. To find the x-intercept, we set y equal to 0. To find the y-intercept, we set x equal to 0. So to find an intercept in general, set the other variable equal to 0 and solve whatever remains. Then you get 2 easy points in order to build a graph. So let's look at another example. So we're given negative 2x plus y equals 0. So let's just find some intercepts. We can build a little table and then plot some points. So let's find our y-intercept by setting x equal to 0. We can say when x equals 0, this would be negative 2 times 0 plus y equals 0. Well, notice this will just give us y equals 0. So that gives us the point 0, 0. It's kind of a double intercept. That's the point at the origin in the middle. So this already tells us when y equals 0, we should also get x equal to 0. But let's just plug it in and see. Let's say we didn't expect that, and I want to find the y-intercept. Or I want to find the x-intercept. When y equals 0, we would say negative 2 times x plus 0 equals 0. So negative 2x equals 0, but then dividing the negative 2 over, we just get that x equals 0. Get that same point again. So in this case, it's going through the origin, so both the x and the y-intercepts are the same point, basically. So we need to find some other points. So sometimes the intercept method may be less useful if you're going through the origin like this. So let's just pick some easy values. I'll pick positive 1 for x. So I can say when x equals positive 1, this would be negative 2 times 1 plus y equals 0. So negative 2 plus y equals 0. Add the 2 over, y equals positive 2. You should have the point 1, 2. And then let's pick negative 1. And we can choose any values we want. Just picking something that seems like it'll be easy. So when x equals negative 1, I would get negative 2 times negative 1 plus y equals 0. So that will give me positive 2 plus y equals 0. then I would subtract that 2 over y equals -2. So I should have the point -1, -2. Let me make this a little smaller so we can have some space here for our graph. So I got 3 points we can work with. Let's plot these. So here we're kind of using a combination of these two methods. We did find an intercept, but it happens to be both the x and the y intercepts. So we needed at least one other point. So we got 3 for good measure. So we can start with the point 0, 0. It's right in the middle. Then the point 1, 2. So 1 on the x-axis, and then up 2, positive 2. So we should be up here. Oops. So we can already see the shape of our line, but let's plot our third point and just see if it makes sense. So we should have the point -1, -2. So this time I'll go -1 for x, so over 1 in the left direction, and then -2 for y, so down 2. So we should end up down here. And that looks pretty good. That looks like it's lining up with our other 2 points. So we'll have some slanted line going through the origin center point. Let me make this a little bit nicer. My scaling is a little bit weird, so that causes it to be slightly off, but in general, it looks pretty good. Let's label our points. This was 0, 0 in the middle. This was our point 1, 2, and this was -1, -2. So if the intercept method fails you, if you only get 1 point out of it, just pick a couple other easy values to plug in and find. All right, let's look at 2 special kinds of lines we can get. So this is graphing linear equations of the form x equals a and y equals b, meaning we only have x or y. If we have something that looks like x equals a, like our first example down here, x equals -2, it's going to be a vertical line, some line that's vertical. So vertical meaning it will look something like this. And if our line just looks like y equals something, it's going to be a horizontal line, because the y value will always be the same, and then it doesn't matter what x is. We saw something like this in terms of a table in our last video. Let's look at 2 examples, and that will make this make a little more sense. Let's first look at example 4. It says, graph the line x equals -2. Well, there's no y to plug into. And it's already solved for x. X is just equal to -2. So there's nothing really to plug in. Let me add my divisions here. So let's imagine where x equals -2. That's over here. So what this is saying is x will always be equal to -2 regardless of what y is. So this is going to create our vertical line going through -2 on the x-axis. So we can imagine, we can imagine any point on this line, like -2, 0, or up here would be like -2, +4, or down here, -2, -4. The x value will always be -2, and that's what this is saying. X is just equal to -2. Y can be anything. This is our x and this is our y. So when you have x equals something, you get a vertical line going through that point on the x-axis. And we can make a similar argument for a horizontal line. Y equals 3. Let's build another graph. now we have y is equal to 3. So I can imagine on the y-axis, up at positive 3, imagine a point there, and then a horizontal line going through positive 3. So we can imagine this is the point 0, 3. We could have this point here, which is 3, 3, or maybe over here, this would be negative 1, 3. Y is always equal to 3. So it can be a little bit tricky because when you see y equals 3, it's tempting to think it's a vertical line because our y-axis is vertical. But what this is saying is that every coordinate point, the y value will be equal to 3. And that produces a horizontal line. And x is kind of free to be anything. We can move any direction in the x-axis or in the x direction, and y will always be 3. So x equals something gives you a vertical line. Y equals something gives you a horizontal line. Something to look out for. If you see these, you can get the graph pretty quickly. All right, in our last example, we have another applied situation. So let's model some data with a linear equation. So example 6 says the annual cost of college tuition and fees at a private four-year institution can be modeled by this equation. Y equals 1,172.5x plus 24,909, where x is the number of years after 2013 and y is the cost of tuition and fees. So I'll say x equals number of years after 2013. So that's something to keep in mind. If x equals 1, that means we're in the year 2014. So I wouldn't plug in 2014, I would just plug in 1. So we have an equation. Part A asks us to find the y-intercept and to explain its meaning. So remember, to find a y-intercept, we set x equal to 0, or plug in 0 for x and solve for y. To find an intercept, plug in 0 for the other variable. So our equation was, let me copy it down here, y equals 1,172.50x plus 24,909. So we're setting x equal to 0, so y equals 1172.50 times 0 plus 24,909. Well, that will just delete that term on the left, so y will just equal whatever's left over, the 24,909. So our y-intercept will be on the point 0 was our x value, and then 24,909 was our y value. But what does this mean? This model or this equation represents something. We said it represented the cost of college of tuition and fees, the annual cost, so for 1 year, where x was the number of years after 2013. So since we plugged in 0 for x, that means we're in no years after 2013, meaning in 2013, this is how much the college costs in that year, 2013. So I can interpret this as the cost of college, the cost of tuition and fees in 2013 was 24,909. cost a lot of money. But yeah, 0 years after 2013, meaning in the year 2013, this was our cost. So from this interpretation, this tells us that as x increases, we're going to increase by multiples of almost $1,200. It's going up by like $1,200 a year. You can view it as a rate of increase, and we'll use more of that language in our next section. All right, let's look at part B. B asks us to find the approximate cost of tuition and fees in 2014 and 2017. So let's make some space. So just remember, x is years after 2013. So to get 2014, that's just 1 year after 2013. So I would want my x value to be equal to 1. This represents the year 2014. So let's just plug it in and solve for y. So the equation was 1172.50 times x, so I'll just plug in 1, plus 24,909. So that'll just give me the same value. So adding these two together, you should get 26,081 and 50 cents. Let's write it as an ordered pair. We'd have the point 1, comma, 26081.5. That's how much it will cost 1 year later in 2014. Seems like a long time ago now. 2014, another world. All right, what was the next date? We wanted 2017. So that's 4 years later. So I can say when x equals 4. This represents 2017. So let's just plug it in. Y equals 1172.50 times 4 plus 24,909. So multiplying that out, we should get 4,690 plus 24,909. Then adding those together, should get 29,599. So as a coordinate point, that would be 4, 29,599. Notice the cost is increasing as the years go by. Part C wants us to graph this, so we do have a couple points. The numbers are quite large. Let's build a little table of values. This is for part C. We can build x and y values on a table. When x was 0, we just had the 24,909. When x was 1, we got 26081. When x was 4, we got 29,599. And it's asking us to graph this, so it'll be a little bit tricky. We have very small numbers for x and very large numbers for y. So we'll have to see how we can label our axes. We might need to do some rounding here. We definitely can't go up. We can't make like 29,000 little tick marks. I mean, we could if we really tried, but we're kind of lacking the space here. I'm going to try and squeeze it into this graph. I know for my x-axis, I want to just go out to 4. We'll do 5, just for good measure. So how can we label our y-axis? Well, let's kind of round these to approximate numbers. This is about 25,000. This is about 26,000. That's what this symbol means, this little double wavy line. It means approximately. It's sort of like, instead of saying equal to, it's like kind of equal to. It kind of has that feeling like you're shrugging your shoulders or something. Wavily equal to. So 29,599, that's like kind of equal to 30,000. So let's say each tick mark means 2,000. So this could be like 2, 4, 6, 8. This would be like 10,000. I'll just say 10K. Then 2, 4, 6, 8. This would be 20K. 2, 4, 6, 8. This would be like 30K. 2, 4. That should about get us there. This will be kind of a rough graph, but see if it will at least give us an idea. So we want the point 0 and then about 25,000. So that would be somewhere here in between. Oh, wait, no, I'm one short. So if they're by twos, this would be 22, this would be 24, this would be 26. So 25,000 is in between. So like 2.5 marks, somewhere here roughly. Then at the point 1, and we're labeling these just 1, 2, 3, 4, 5. At 1, we're at about 26,000. So we're just a little bit higher. And then at 4, we're close to 30,000. So let me see if I can line this up right. About right here, just as a rough guess. So the cost starts pretty high, and then it continues to grow a bit each year. I guess they raise their prices, inflation happens, things just tend to get more expensive over time. It's the overall trend. So not the most satisfying graph, but we can maybe even do some additional graphing tricks to make it more visually appealing. But we do get the sense of it starting at a pretty high cost and then increasing at some constant rate as time goes on. What did part C or part D want? It says use the graph to approximate the cost of tuition and fees in 2018. Is it the same when you use the equation? So let's use the graph. 2018, that would be at 5 on our x-axis. My 5 looked really weird. And let's see, this point for 4 should have been a little bit, I think, over. If I imagine a straight line, it should be like right here. So yeah, if I imagine a straight line coming up from 5, my graph is very rough, but we can maybe get an approximation. What is that approximately equal to? Let's see. If this was, let me make this a little bit better. Let's see. I want to go straight across. So maybe like if this was 30K here, it's like a little bit more than 32. Let's just say approximately 32,000. Again, my graph is very rough. My spacing was a little bit off, but we're just getting an approximation. So I can say in 2018, this is when x is equal to 5. From the graph, let's say our estimate is approximately 32K. But we have an equation, so if I really wanted to know, I would just plug in 5 for our x value. So let's plug it in. Let's say y equals, the equation was 1172.50 times x, so this time x will be equal to 5, plus 24909. So multiplying that out, 1172.5 times 5, I get y equals 5862.5 plus 24909. Let's add those together. And this gives me the exact answer, which is a little bit less, 30,771.5. So kind of close to our approximation. We're still off by a little bit, and that's due to the trying to cram all these values into the graph. Might think about making better spacing for the y-axis next time. You can skip a bunch of values by adding like a squiggly mark on the y-axis. And maybe we should have done that and started. It would give us some more room to add in like smaller increments in these values. That would give us some more precision. But since we had the actual equation, we can find the exact solution. This is the most accurate solution since we have the equation for the line itself. So we were close, but we were off due to accumulation of errors in graphing. Yeah, you can see even my distance between 4 and 5 was a little bit more, so maybe 5 should have been a bit closer. That would have put us a bit closer to this 30K mark in the end. But again, we were just approximating. But just to show some application of using the graph of a linear equation in order to model some real-world situation, the ever-increasing cost of tuition. All right, so that's it for 3.2. So we were graphing by plotting points. We graphed by finding intercepts. We graphed a line that goes through the origin. We saw some vertical and horizontal lines. And we finished by modeling some data with the linear equation. So that's it for this video. Next time we'll be looking specifically at that rate of change of the line, which we'll define as the slope. So I'll see you then. Take care.